Hello everyone. Today Frederico Cançado from UFMG will tell us about the quotient graphs and the stochastic matrices. Please.
Oh, hello, it's a pleasure to be here. Thanks for the invitation. Today I'm gonna talk about graphs that have like special structures in them, like regularities. It's not always, the regularities not always come from symmetries, as we're gonna see, but sometimes they do come from symmetries. I'm gonna define it precisely later, but like when you have some types of regularities, you can take different kinds of quotients in the graphs. And, and there are basically three types of quotient, and I'm gonna discuss about them. Like the first one is already discussed by literature. It has like a very clear theorem about equivalences between two graphs having a common quotient. And then I'm gonna talk about the other two type of quotients, why they are interesting, and like how can we use, and some theorems that me and Gabriel Coutinho have come up to characterize when we have the two graphs with some common quotient. In the middle of the process, it will appear naturally the stochastic matrices. A matrix is said to be stochastic if their lines sum to 1 or if their columns sums to 1. We'll be talking about doubly stochastic matrix, which is they are stochastic and their transposed is also stochastic. Or sometimes just like matrices that are self-adjoint, so we do not distinguish between like stochastic or double stochastic. But they are also useful because like the rows or their columns will make like a probability distribution, so you can use them in a lot of meaningful ways besides this theory about quotient graphs. So this is a structure in a graph that I will talk about later, but I find it very interesting. The motivation about this problem, I will first present the motivation that made like Ullmann one of the first guys to make the characterization theorem to study them. So we have a decision problem that is how do we decide whether two graphs they are isomorphic? Here we're assuming that the graphs they have the same number of vertices, because if they don't, they are clearly not isomorphic. So this problem is very difficult to compute. People still do not know like whether this is NP complete or P or like in between. Most people, I think, believe this problem is neither like not in P or in P. There is like a sub-exponential computation, but there are non-polynomial computations to decide when two graphs are isomorphic. So we'll begin to address this problem like with some tools from linear programming, and then we will relax these tools and we will arrive to a concept that is weaker than isomorphism. But this concept will have to do with the quotient that we'll talk in a minute. So this problem is difficult, and it can also be given in a matrix form. Like if we have two matrices, when there is a permutation that we can kind of we can multiply one in the right and the other in the left and obtain equality. So this is equivalent to the initial problem because we can have like the matrices can be the adjacent matrices of graphs, and we can also talk about weighted graphs with isomorphisms. So this is exactly the same thing, basically. So we can also rewrite it in the form of integer programming computation. That is, we want to see if there is a matrix P with coordinates 0 or 1, such that this linear restriction happen. We see that multiplying a matrix is a linear process, so this is linear. So the problem of this programming is that we are dealing with integer, so it's not, there is no clear algorithmic way to see whether there is or not a matrix that satisfies this. Like the problem of integer computation is NP complete. It's actually harder than the graph isomorphism problem. So we have begun like with a simple problem, and now it's kind of a perhaps a stronger problem. It's the same problem in this case, but like we have formulated these in the language of a stronger class of problems. So this is not very good at first view, but then we can kind of relax this problem. The main restriction here that is causing all the trouble is that the coordinates, they are integer. So we may also want to have like non-integer coordinates. And so this will not be an isomorphism anymore. This will be what we call a fractionary isomorphism. So it begins with the relaxation of the problem. And now we want to solve this other problem, that is P is doubly stochastic, is in the double stochastic polytope. So the double stochastic polytope is all the matrices whose lines and whose columns sum to 1. But this is very good for our computation because this is a polytope, it's convex also. So we have like an algorithm that solves these in polynomial time up to precision. And we recall that by Birkhoff's theorem, this polytope is exactly the convex hull of the permutation matrices. Well, the Birkhoff's theorem basically says that any double stochastic matrix is a linear combination of permutations. So now we have taken basically the convex hull. It makes the problem easier, but it also creates solutions that are not real isomorphism. So a class of examples that is very clearly not an isomorphism is when you have two graphs that are k-regular. If we multiply it by j is the R1 matrix here. We, as both of them has 1 as an eigenvector, the R1's vector has an eigenvector, we only like we maintain the one in the one here in the J, and we have the K going out as the eigenvalue. So this works for both sides because of they commute, like they are. We can also take the transpose to see that. But it's very clear that this is not what we wanted at the first sight, but it's an interesting phenomenon that is like that we have this kind of weaker isomorphism thing that we can compute very quickly, but it's not always a real isomorphism. It's called fractional isomorphism. So we have here, we have like a test for when two graphs, they are not isomorphic. If they are not fractional isomorphic, then clearly they are not isomorphic, but like the converse is strongly false, and we presented a very huge class of graphs. It will become later evident why this works for the regular graphs. We will characterize all the graphs that are fractional isomorphic. So Another problem that also comes as a relaxation in the problem of deciding graph isomorphism is the vice-fellow graph isomorphism test. Here I'm talking about one vice-fellow. There's like many dimensions vice-fellow. We can talk about the one vice-fellow, two vice-fellow, and I will say briefly what the higher dimension are in a second. So this is a more combinatorial way to see if the graphs they are as isomorphic, and it's based in the number of neighbor of each vertex. But we don't only get like the first number of neighbor, then we get the number of neighbor that each neighbor has, and then we take this recursively. And this forms like a vector, a big vector. But the way that we do this, like in a programming way, is that we start by making classes of equivalence. We start by all the vertices, they are like the same in the same class, and then we say if two graphs, uh, if two vertices they have a different number of neighbors, they must be put in different classes. So here is the first iteration of the program. Like this vertex here, it has two neighbors, and this has two neighbors also, so they go to the same class. This one has three neighbors, so it goes to another class, and the other has only one neighbor. So now we are gonna look iteratively to this. Like this one has one neighbor that has two neighbors, so it goes to a class, and this one has one neighbor that has three neighbors, so it goes to another class. And we keep repeating the process, and we get like we will get like finer partitions of the graph until we eventually stabilize. It is clear that it must stabilize because at each repetition, if nothing is changed, we will never change anything forever. And at each repetition, we kind of put a vertex in another class. So at most, at n iterations, we'll have an unstable partition of the graph. It's not always the trivial partition. Also, like in this case, we have that these both vertices they are in the same partition. And so if two graphs they have the same structure of the stable partition, we'll say that they are that the vice-fellow lemon will say that they are isomorphic. And again, this does not correspond to real isomorphism. This is actually equivalent to the fractional isomorphism that we have seen. For instance, if we get any graph that is regular, each vertex will keep in the same class forever because they all have the same number of neighbors. So we are not changing it, and it's already stable. So we have only one partition, and all the vertices that are regular with the same number of neighbors, they are going to be identified as they are gonna pass the one vice-fellow lemon. The vice-fellow lemon was very well studied. There is higher dimensional that we start with tuples of vertices instead of only one vertex. And we kind of iterate the same process, but seeing like the neighborhood of both vertices at the same time. And the difficulty to compute it kind of increases when you grow in the dimension. But it's already proven that for any dimension, we have two non-isomorphic graphs that will pass this dimension. So we already know that, like, for any big enough dimension, and the vice-fellow will not be a polytime algorithm for differentiating non-isomorphic for the isomorphism of graphs. So now we are going to present like the first theorem that will bound together the both results that we have talked. That is, if we have two graphs with the same number of vertices, this is actually very important in this theorem, because later we'll talk about graphs that have different number of vertices and how they can behave alike in some sense. So we have the equivalence between there being fractionally isomorphic. They pass in the one Weisfellow-Lemon algorithm, and also they have in some common equitable partition, and they have also in common the coarsest equitable partition. So equitable partition will be this type of regularity that graphs have that we are interested in this seminar specifically. So I have kind of delayed the definition for a while, so we can talk about regularities and everything without seeing the definition exactly, and it will become clear how it appears in all these contexts. And we will also talk about an order of partitions that we will have naturally in the set of equitable partitions of a graph. So now the main concept. A partition, which is we only get all the vertices and put them into some sets that we call cells. It will be called equitable if the number of neighbors that each vertex have in each cell only depends on the cells that we're talking. It does not depend on the vertex. So intuitively, like if we restrict the graph to two cells, it will behave like regularly, like a bipartite regular graph. The vertices between the cells, not the edges between the cells, not like within also. In each cell, the graph will also be regular because we can have R equal to S in here. And so what we want is, if we give like an address that is a cell, another address that is the other cell, we want the number of neighbors that each vertex from the first address having the second address to be the same. So it's a very regular condition. It's a regularity condition. We have also that a partition is invariant with the one Weisfellow if and only if it is equitable. So I don't know if it's clear at this stage, but like the Weisfellow only care about like the neighbor of each vertex and the neighbor that each vertex have in like each class, and this recursively. So if we have an equitable partition, the number of neighbors that are each vertex in this cell will have in any other cell, or any recursion of it is constant because of the definition. So here I have put two examples that are interesting of equitable partition. The first one, we have the cube, and this is also the distance partition of the cube. So I will talk a little about, like I will just comment on distance regular graphs, but it is basically for any fixed point in the cube, we have like the same distance partition. The distance partition is like we have the vertex that are zero distance from the fixed one in a cell, the ones that are one distance in another, two distance in another, three distance in another. So if all the distance partitions, they are equitable and they are equivalent for all the vertex, the graph will be called distance regular graph. And that is they are very well studied. This is a very well studied class of graphs. Like, they have very important properties and they are used as strongly regular graphs to construct other structures in mathematics. And well, I'm just leaving that as a like some insight in other theories that kind of have relation with this. So this other graph is the first, it's the smallest graph that have an equitable partition that do not come from a symmetry class, from an isomorphism subgroup. Like if we fix any subgroup of the isomorphism group of a graph, we can take the orbits of each vertex by this group, and these orbits, they will have like very nice properties, and they will be regular, and they will also form an equitable partition. But it's not always the case. The equitable partition is basically a regularity condition. It's not a symmetry condition. And in spite of, this example, you can think of a group that kind of permutes the vertex here, and they form these as the orbits of the group. But here we cannot. We do not have a subgroup that will leave us with this partition in particular. So this is like a relevant graph to show that this study is not actually a study in the isomorphism group. Is another phenomenon of the graph. So now we will have also another interesting structure in the equitable partitions. That is, we can compare them in some way. We can put like a partial order in them. So we'll say that one partition, it is coarser than the other. If the first one, each cell of it contains entirely, each cells of the second one, of the final one, is contained entirely in the cell of the first one. So like they are compatible in some way. We do not have cells that like they are distinct, but they cover different elements. Like if a cell of one of the coarser one touches the cell of the finer one, it will cover it entirely. So this is a way to guarantee that we can compare like the points, because we are not like breaking the cells in the middles, which could lead to something that is not equitable. Well, and it is denoted as the inequality. And also the partitions, they form a structure that we call lattice with respect to this order, which means that for two equitable partitions, we always have a supremum and an infimum, which the supremum of two equitable partitions, it's the meet of the partitions, because normally in a graph partition, we also, for any partition, we have this order. Like, we do not use that this is equitable to define this order. So we can define this order in all the partitions of a set, and then we can define the join and the meet of two partitions. The meet is basically, we get like two partitions, and we put one over the other, And if two cells touch, we kind of merge it in one cell. And we do that with all the cells that are touching. So this is also called the closure, the transitive closure of the union of the relation. But we do that in order to guarantee that the equivalence will continue to be, that the relation will continue to be an equivalence. So we can do that for any partition. And in particular, when we do this for two equitable partitions, the result will also be equitable. So as we have this operation that is called meet, and we will also have an minimal partition that is the trivial partition, which is always equitable. We have that this structure, it forms a lattice. So this is the example of the start of the PowerPoint that we have. Like this is the finest equitable partition. It is smallest than any one, and then we have like these intermediary equitable partitions. They do not relate between them. Neither of them are coarser than the other, and they are all coarser than this coarsest equitable partition. And as the equitable partition is closed by meet, we can always have like the coarsest equitable partition, which is actually what the Weisfeller-Lemon compute. It is the coarsest equitable partition. So now that we have talking about equitable partition, we arrive naturally to the theme of quotients. And the quotient is what I have said earlier. We have like a graph, we have the partitions, and we want to like each cell now it is very regular, so we can kind of think it as of a vertex instead of a set of vertex, and this will lead us to the quotient. So the quotient will be defined having vertices as the cells, and it will be a directed weighted graph, because it's not always symmetric, the relations between the cells within an equitable partition. And so we define the weight of the arc Rs as the number of neighbors that a vertex in the cell CR has in the cell CS. So this is the definition. We can now also symmetrize the graph that we obtain, and we just get like the geometric mean of the arc that is going from R to S and from S to R. And we get the mean, the geometric mean, because this is equivalent to, well, conjugating the matrix of the graph. So the graph, the matrices, the adjacent matrices, they will be similar, which is very useful because they maintain spectral properties and the characteristic polynomials and all of the, well, everything that we wanted for it to have. So as an example, I put again the cube here with that partition in particular, and we have like one from the cell white to the cell blue. We have three vertices, which means this vertex has three neighbors in the cell. So here it will be an arc of value 3. And we see that in the opposite direction is not the same, because each blue vertex has only one neighbor in the white cell. So we have this arc as 1. And then we take the symmetrized version, which is the graph, which is only we are making this graph we're making a digraph into a graph, a weighted graph only. So we simply take the mean. There are also some other characterizations, like we can characterize by doing some matrix product with respect to the product that indicates the matrix. But I will just put like the most combinatorial one, which I think it's more clear. But there are a lot of tools for doing these quotients. So we have now a characterization of when two graphs they have a common quotient. So this is not the same as we had before with the Ullmann et al. Theorem, because now the graphs they can have different number of vertices and the same quotient nevertheless. So we see that the conditions they are a bit weaker also. So the following are equivalent. There are equitable partitions such that the quotient of the graph, the directed quotient is isomorphic, or also they're being isomorphic for the courses equitable partition. I think this is a new result also, because I didn't see in the literature like people studying a lot the people citing these specifically, because normally there was the order that if they have the same some common equitable partition, they have the same courses equitable partition. But this allows for the case of the graphs with the same number of vertices. Well, they also can have a common cover. This is also like I put this as it's not our result, it's a non-result actually from the literature. I put this as a motivation, like a combinatorial motivation of why do you want to have why do you want to study this? What does it mean in terms of like walks and combinatorics? So a common cover, it can be, I'll not define it here, but it can be thought about like some graph that locally preserve the structure of both maps. So have a cover for one, and this is also a cover for the other. So it is locally respecting the number of neighbors that each vertex have, and other properties. Well, it's a kind of a it's a non-trivial definition. It will take some time to read, but I think it's very cool that the equitable partitions appears also in the cover theory. And now we have our description of when there is a common quotient using a matrix. That is, we have a matrix M with constant row sum and constant column sum, such that AXM is equal to MAY. This is interesting because this is kind of well, the matrices that have a constant sum and constant row and constant column sum, they are a convex set. So we can use the linear programming technique to determine if there is an equality in here. And we observe that this matrix is not square matrix, because now the dimension of A and the dimension of AX and Y are different. So we cannot demand it to be double stochastic, but we can demand that the lines all sum to some constant which is different to the constant of the rows. Well, we can always normalize both constant by some constant also, because if we put some normalizer in here, the equality is still maintained. So it's not as restricted as it may seem. We also have this theorem about how the lattice behaves when it takes the quotient, which we couldn't find any reference of it in the literature, and we have proven in the paper. So it is similar to like when you take a quotient in a ring, the rings that are contained, the ideals that are contained in that contains the ideal that you are quotient, they pass to the quotient. So in this case is the equitable partition. If we have like an equitable partition that is coarser than the fixed equitable partition that we're taking the quotient, this one, then it will pass to the quotient and will pass naturally, because like the new in the quotient we have not vertices, we have like cells defining the vertices of the new graph. But like each cell is contained entirely in one and only one cell of the coarser partition. So we just define a new partition that is the partition of the cells contained in the cells. That's why it's important to have like the coarser relationship. And so when you take the quotient, it passes. An example here is the cube again. That if we take like the first unsymmetrized quotient, we see that the cube is also three regular, so it has one big partition that is all the vertices. So when we take the first quotient, the resulting graph is still three regular. So we can take another quotient in this graph, and also if take two quotients is equivalent to take only one. So, well, this is like an example. We unfortunately do not have this for the symmetrized case, because like this graph is not regular. So we have lost a partition. This will imply some things about the last relationships between graphs that we'll talk in a second. Well, now it's the symmetrized quotient. I started studying it for studying perfect state transfer, which is very useful for quantum walks in graphs, and it is being like studied for quantum computation as well. The main theorem involving PST is that if we have like a well-behaved partition, and in the quotient we have PST, we also have PST in the original graph. But we have to have one more restriction, that is the vertices that have PST, they must be cells corresponding to only one vertex. Otherwise, we do not keep the phenomenon. We would have some kind of like all the vertices in the class, they kind of move to another in some quantum walk state, but it is not what we desire to study. So this technology kind of motivates us to build graphs and then kind of pop them up to other graphs that also have PST. And this is one motivation for the symmetrized quotient. Well, the spectrum is also well behaved because the spectrum of the quotient, it is contained in the spectrum of the original vertex. We have a lot of spectral applications of the symmetrized quotient, and also weighted quotient, which I will not talk today. But we can find a lot of eigenvalues bounds for the graph if we have information on its quotient, in its symmetrized quotient. Well, now it's problematic that the lattice is not preserved when we take the symmetrized quotient, because we can create or destroy like new, we can create or destroy partitions that were not in the original one. It's also not an equivalence relation. It would not be transitive. Like the thing that guarantees that the quotient is transitive is basically this theorem, because if we can take a quotient from one to the other, it can, and from another to this, and from this other to a new one, then we can take like only one because of how it passes everything neatly. But now we do not have like this guarantee. So we can have like a graph that has a common symmetrized quotient with another, and this other has with the third one, but the first and the last, they do not have a symmetrized quotient. And they are also very like these examples, they are not very difficult to find. So here is one, like we have a quotient from this one to this one, have a quotient from this one to this one, but like these, they do not have but there is no quotient that take like these and these to the same. Oh yes, like we have a quotient both from this to this, but we do not have like a quotient from this to this, which is, well, what we would not have in the other case. We have also a characterization of the symmetrized quotient, which involves matrices, but it's not computationally easy to calculate, and it's not very complete, this theory, because we do not have like a combinatorial characterization and the other things that we like to have. But you have one with matrices that is, they have some they are isomorphic with some when symmetrized quotient to graphs. This is equivalent to, we have a matrix M such that it multiplies at the right ax and gives us the ay multiplied by the left. And now we have a restriction which is not very trivial, that is both M times M transpose and M transpose times M are double stochastic. So this is equivalent to this. And I yet do not have like a very good characterization of which matrices would satisfy this condition, but it's an infinite leaf condition. We also have it's also easy to compute which matrix M it would be if we had the partition of X and Y. So now the conclusion is that it's just a table that we will summarize everything that is. We were researching when we have a common quotient between two graphs. If the quotient is the non-symmetrized one, and the graph they have the same number of vertices, this is already well characterized by the literature. Combinatorially, it's equivalent to have them both pass the one Weisfellow lemma. And we also have the matricial characterization that is a double stochastic matrix that semi-conjugates them. Now, if we remove the restriction of having the same number of vertices, we still have a combinatorics characterization, which is a common cover between them. And we have a matricial condition, which is we have an M that semi-conjugates, but now we weaken the double stochastic condition. We can have like the lines and the rows summing to different constants. And this will be necessary because the matrix is not square anymore. So we cannot demand it to be double stochastic. And if we have some partitions such that the symmetrized graph is isomorphic, then we have no combinatorial characterization of it, which is, well, I have tried, Gabriel also have tried, but we cannot find any yet. But we have a nice matricial condition, which is this involving the matrices that are not per se stochastic, but they are stochastic when you compose with its transposed. So that's it. Any questions?
Thank you, Frederico. Do we have questions for Fred? Could you show the previous page, please? So for the first one, you said it's polynomial testable.
The what?
There's a polynomial time algorithm for the first one.
You mean the one Weisfellow or the linear programming?
Yeah, the first one.
Oh, yes.
How about the other two?
Oh, if you have a... So I have not thought about, I think we can, this one, we can, is also a linear programming. I'm not sure about, like the constant of the rows and of the columns, it can be kind of fixed depending on the size of the matrix, because we can double count it in some kind of way. We can also normalize it. So I think it is linear programming. But this is like a up to precision poly algorithm. I don't know if having an up to precision we can take like an exactly one.
So for the second and the third, are the matrix does the matrix M have to have a non-negative entries, or there's no restriction?
Oh yeah, all the matrix M they are non-negative. I'm sorry, I forgot about
Okay.
that. This
Yeah.
is very important.
Yeah. Thank you. Do we have other questions for Fred? Yes. So,
Hi, Fred. Thank you for a nice talk. So I'm interested in regular graphs. What is this M for regular graph? Is just J, or you can get something else also?
So this M depends on the graph and the partition. I mean, for the regular graphs, all J's will serve like not J normalized, but well, but also if they have some other equitable partition in common besides the regular one, we can get another M. Like I did not talk much about the proofs, but the structure of M, it gives us the partition. The partition will be like in the composable blocks of the matrix M. So each partition we can get a different M. We have many M's for the same also, but if the graphs they are regular and they have a common partition besides the all vertices partitions, then we have other M's besides the all one.
Okay, thank you. Thank you.